One of the uses for percent compositions, aside from difficult two variable problems or looking at being able to use that number as for dimensional analysis, is empirical and molecular formula determination. I really like this portion of chapter 3 because we get to talk a little bit about combustion analysis, which is how some organics are derived, or at least their masses are derived in reality. So an empirical formula is the simplest ratio of elements in a compound. For example, benzene. Benzene has the formula C6H6. That is not an empirical formula because these numbers can be reduced. And so the empirical formula for benzene is CH. You might be asking yourself, well, why do that? Well, a lot of the analysis that's done in reality will only give you the ratios, right? Because essentially what we're going to do is we're going to take mass ratios and compare them to one another to get small whole numbers. A molecular formula would be the scaled up portion, where we have values that match with whatever it is, okay? With what the thing is in reality. So in order to do empirical formula calculations, the first thing you should do is get everybody into masses. So if you have carbon and hydrogen and whatever, you just convert them into masses. Usually this happens by percents. And the way that we do this is by assuming 100 grams. So if I have 10.1% of fluorine and I say I assume 100 grams of the compound, that means that 10.1 grams of it is fluorine. Once you have gotten everybody into masses, convert the masses to moles. Then you can divide everybody by the smallest value. The reason why we do this is effectively what we're doing is we're saying, okay, one of these guys is going to be 1. What is the ratio of everybody else to 1? And then from there, we can't have fractions of atoms, so you use this chart. If you have something like 2.01, then go ahead, it's 2, right? If you have 2.09, it's 2. If you have 2.25, it is not 2. What you do then is you multiply the entire molecule by this number to get a whole number ratio. So let's try this out. I have a sample that contains only phosphorus and chlorine and is found to have 1.968 grams of phosphorus. Determine the empirical formula. Okay, so question 1. I got to get everybody into masses, so how do I get the mass of chlorine? Well, what we do is we take the original mass, this 5.347 grams of compound, and we subtract out the phosphorus. Why does this work? Well, the law of conservation of mass. We are saying that, okay, all of the mass is composed of phosphorus and chlorine. If I know the mass of phosphorus, then I can determine the mass of chlorine. And so I end up getting 3.379 grams of chlorine. I now have both species present as masses. I have phosphorus and I have chlorine. The next thing to do is convert them into moles. So I have 1.968 grams of chlorine. I have 3.37, other way around. Let me get rid of that, phosphorus, not chlorine. And I have 3.379 grams of chlorine. I'm going to convert these both into moles. And so with chlorine, again, we're doing elements that are present in a compound. So this isn't Cl2, it's Cl. So that's straight off the periodic table, 35.453 grams to 1 mole. For phosphorus, we have 30.97376 grams in 1 mole. Multiply across the top, divided by the bottom for each. So on top, up on phosphorus, I have 0.06354 moles of phosphorus. And down at this one, I have 0.095309 moles. I now pick the smallest one so that I can make a ratio. That's going to be the top, 0.06354 divided by 0.06354. This becomes 1. This becomes 1.4999. So currently I have phosphorus 1, chlorine 1.4999. So in order to get this to be whole numbers, I multiply this by 2. And so I end up getting P2Cl3. My empirical formula should not be reducible. If it is, you need to reduce it down. And if you get it and it's reducible, you might want to go back and check your math. You may have screwed up on something. So this is the empirical formula, but it might not be what it is in reality. Reality is the molecular formula. So for example, benzene, right? We would determine from experiments that it has a empirical formula is this. Its molecular formula, though, would be this, how it exists in reality. So in order to find the molecular formula, the first thing you do is you determine the empirical formula. You then calculate the empirical formula mass. So you take, basically you're doing like you would do with the molar mass or the molecular mass. And this would be 12.011 plus 1.00794, right? And so this ends up being 13.018, so on and so forth. You will then be given the molar mass of the molecular formula. And what you do is you take the two, you divide them, and you get what's called an N value. N is the number you multiply the empirical formula by to get the molecular formula. So this should be a whole number. If it's not close, like within 0.1 of a whole number, you messed up. Check your math. So let's do a calculation with this that involves some percents as well. So I have an organic that is made up of carbon and hydrogen, and it has a molar mass, which I'm going to have to give to you, although later down the road, you may have to figure that out using other techniques. For example, gas law. That's one of my favorite problems. So I'm going to give you the molar mass, right? This is the mass of the molecular compound. And also as a note, the N value can be 1, right? Because that would mean that the molar mass of the molecule and the empirical formula mass are the same. So the empirical formula is the molecular formula. So that's the molecular molar mass. All right, step 1, convert everybody into masses. So I'm going to assume 100 grams of compound. So that means I have 83.6 grams of carbon and I have 16.3 grams of hydrogen. So once I have everybody converted into masses, the next thing to do is to convert into moles. So 12.011 grams, 1 mole C, and 1.00794 grams, and 1 mole H. Okay. So this ends up being 6.960 moles. This ends up being 16.16 moles. Divide by the smallest, 16.960 moles. Divided by 6.960 moles. And I end up getting 1 and 2.32. Okay, so right now I have carbon 1 and H 2.32. So in order to get this into whole numbers, I'm going to multiply this whole thing by 3. So this becomes C3H7. Now we need to get the molar mass, the empirical formula mass. So here I calculate out carbon, which is 3 times 12.011 grams per mole. Hydrogen, which is 7 times 1.00794 grams per mole. Sum these guys up, and I end up getting 43.09 grams per mole. So this is my empirical formula mass. To get my N value, I take the actual molar mass divided by 43.09 grams per mole, and this ends up equaling 2. So that means I take this guy here, multiply it by 2, and I'll get my molar mass, or my molecular formula, excuse me. So C3H7 times 2 is equal to C6H14. This is my molecular formula. This is my empirical formula. Notice the two are different. They can be the same, though. So these problems are very good to know how to do. I definitely include them on my exams. We got one more thing to cover in empirical formula and molecular formula, and that's combustion analysis, which is by far my favorite for this little section. So combustion analysis is a way that we can determine the composition of an organic. Essentially what you do is you take an organic, you put it into a furnace, and then you have these filters that change. You mass them before, you weigh them before, and then you weigh them after, and that tells you how many grams of whatever was captured. So for example, in the first filter, H2O would be absorbed. In the second filter, CO2 would be absorbed. There's also filters for N2 and SO2. So in these filters, all of the carbon goes to CO2. All of the hydrogen goes into water. But the real problem comes into oxygen. Oxygen is streamed through at a constant rate so that there's no, or the reaction isn't limited by oxygen. So we don't know if this oxygen that's in CO2 and water came from the organic or if it came from the O2. The way that we do this is we need a mass to begin with. So essentially, the way that we do it is the mass of O in an organic, if it's present, is to take the other guys, do a little bit of math. The mass of oxygen will equal the mass of compound minus the mass of carbon minus the mass of hydrogen minus any other element in the organic. So for example, if I have an organic that has carbon, hydrogen, nitrogen, and oxygen, the mass of oxygen is going to be the mass of the compound minus the mass of carbon, hydrogen, and nitrogen. So it's best to demonstrate this. The way that you get the mass of the carbon and hydrogen that's present is just through some dimensional analysis. So I have 15.7 grams of an unknown, and it has carbon, hydrogen, and oxygen in it. The scrubbers, which are the name of the filters, have carbon dioxide of mass of 27.1 and water of 8.3. The compound has a molar mass of 200 grams per mole, which is usually determined through things like mass spectroscopy. So just like with any of the other empirical molecular formula calculations, the first thing I need to do is get everybody into masses. So I have 27.1 grams of CO2, and I have 8.3 grams of H2O. Remember, we cannot determine oxygen based on either one of these. What we can do is turn CO2 into carbon and H2O into H. So the way that we do that is first go to moles, then to mass. So I have, let's see here, for CO2, I have a molar mass of 44.0, we'll just go 1 grams, 1 mole. CO2, for every 1 mole CO2, I have 1 mole of carbon. And I'm going to do a quick stop here and get my moles of carbon. I'll explain why later. 27.1 divided by 44.01. And I get 0.615. 8 moles carbon. For water, I have 18.015 grams in 1 mole. Now, for every 1 mole of water, I have 2 moles of H. That's an important distinction. Make sure you don't mess that up. Multiply across the top, divide by the bottom, and I end up getting 0.921. I'll just throw the 4 on there. Moles H. So I'm going to need those later, but I need the masses for each one of these. So what I'm going to do is I'm going to convert from 1 mole of carbon to 12.011 grams of carbon. And for every 1 mole H, I have 1.00794 grams H. And so this gives me 7.396 grams of carbon and 0.929 grams of hydrogen. Why do I need this? Because I need to determine what my composition of this compound is oxygen. So now I go and use the mass of oxygen is equal to 15.7 grams of the compound minus 7.396 grams of carbon minus 0.929 grams of hydrogen, and I end up getting 7.3. Let's see, what's the last sig fig? So that's the last one. So we'll add that one last, because that's the last sig fig gram oxygen. All right, so 7.38 grams of oxygen. I'm going to convert this into moles. So for every 15.9994 grams, I have 1 mole of oxygen. So this ends up giving me 0.4610 moles of oxygen. Now I have everybody in moles. I have this guy in mole, this guy in mole, this guy in mole. This is the smallest, so I'm going to move on down here into red. And for carbon, I have 0.6158 moles divided by 0.4610 moles. For hydrogen, I have 0.9214 moles divided by 0.4610 moles. And then for oxygen, I have 0.4610 moles divided by 0.4610 moles. So this is 1. This ends up being 1.9998, which is equal to 2. And then this one is 1.336. So right now I have carbon 1.336 H2O1. I can't have that, so I got to multiply this by 3. And I end up getting C4H6O3. I go through and I figure out the empirical formula mass, because now I need to get into the molecular formula. And so with 4 carbons, 6 hydrogens, and 3 oxygens, I have a mass of 102 grams per mole. 200 grams per mole divided by 102 grams per mole is equal to 2. So I take my empirical formula, this guy here, multiplied by 2. And so for a final answer, I end up getting C8H12O6, right? So my empirical formula minus my n value, and I get my molecular formula. A lot of work. But I love these problems. You'll probably see one again, maybe on an exam or on the final.